All right. Here I'll talk about Bayes' rule, and this is basically looking at conditional probabilities. And a classic example is a medical example. Might be kind of interesting and relevant for anyone, especially these days, looking at the COVID test. A lot of people with COVID. Here's the question. So using made-up numbers, let's say the prevalence of some disease is 3% in the population. Prevalence means what percentage of the population currently has the disease, not in the past or in the future, just currently how many people have the disease over the total population. So really this is, if we say that people with the disease are in this set D, then people without disease are in this set DC. So the probability of the disease is 0.03 or 3%. Now let's say we have a test for this disease, and if you test someone who you know has the disease and they take the test, then the test has a 99% of the time will give true. Will give true you have the disease. True, the disease exists. If the person does not have the disease, then the test has a 98% chance will give false, that the person does not have the disease. So these numbers look pretty good. The question is, if I take the test and I don't know if I have the disease, and the test gives me true, what is the probability that I actually have the disease? So what you'll find is that it is counterintuitive, and this is, these sets of numbers are a good example for the introductory, probability classes to make a point, is that these two things, these conditional probabilities, there's more to it than meets the eye at first glance. So to find this probability, we're looking for the probability that I have the disease if the test gives me true. Using Bayes' rule, this is equal to the probability that the test is true, given that I have the disease, times the probability of having the disease in the general population over probability of getting a true in general. This is Bayes' rule. I'll give a drawing afterwards, just to show that it makes a little more sense. Give a graphical representation, but this is the rule so far. So what are these values? So if I draw this tree diagram, so in the general population, 3% of people have the disease. So if I put disease here, and the complement to disease, which is people without the disease, this will be 0.03, this will be 0.97, 97%, and 3%. If you take someone with the disease, then there is a 99% chance you return true, and a 0.01% chance 0.01, not 0.01%. 0.01 chance that you'll get false. And on this side, 0.98 for a false, and a 0.02 for true. So as a note, this, if the person has disease and the test will return positive, is 99%. This is also the same thing as saying sensitivity is 99%, and this one is specificity is 99%. It's 98% specific. So let's see these numbers here. This is the probability of getting a true if you have a disease, so that's 0.99, times probability of having the disease, 0.03, over probability of getting a positive response. Now what that is, according to the total probability rule, this PT is equal to probability of T given D times probability of D plus probability of T given DC times the probability of DC. In other words, it is the probability of this length of this tree diagram plus this length in the tree diagram gives you all of our T's here. So 0.99 times 0.03 plus 0.97 times 0.02. It's just this one goes to T, so we find that one plus this one. So the probability here of being in this side rather than this side is just equal to this one over this one plus that one. So if you multiply this, and this gives approximately 0.605. So about 60% chance that if I get a test returning positive, then the probability that I actually have the disease is 60%. So this is a little counterintuitive, where the numbers seem like the test is pretty accurate, but if I actually get a positive, there's actually 40% chance that I don't actually have the disease. So if you think about why, you'll notice that it's because there's a large amount of false positives, as denoted here. So 2% of the 2% of most of the population are going to get false positive. So there's a good chance, 40% of people who take the test are going to get false positive if they return true. Now, one way to kind of graphically look at this is if I have 100 people in total, and if I split this into all these 100 people into the people that don't have the disease and the people who do. Let's say we know the people who do are 3%, so let's just say let's just say this small area over here is people who have the disease, so I label that D, and people who do not have disease is everywhere else, DC. Now we know that 99% of these people, if they take the test, they're going to get positive. So I'm just going to, this is probably not 99%, but let's say this area is 99%, and all of these people are going to get positive. And then in this tiny 1%, they'll get false. On the other hand, DC, 98% will get a false. So let's see if I can say all the way over here, let's say, it's probably more than that. Let's say this. So this 98% here is false, and then this 2% here is true. So what we're looking for the probability that I'm in D if I'm true. So this is the total area for tests that return true. So what is the probability of me being within D over this? And now you can see that, yeah, it's about 60%. So graphically, this can provide some visual intuition as to why this number 60 is so far from this 98%. And what you'll notice is that this depends on the prevalence. So if this was a very rare disease, if this was only prevalent in 0.01% of the population, then the false positives would be even higher. This number would be even lower, maybe like 10% or something like that. So as a practical example, I want to look at the rapid antigen test of COVID. So let me see here. Copy this on here. Let's take a look at this. This was published last year in August. Diagnostic accuracy of SARS-CoV-2 rapid antigen test. So for COVID, there are multiple tests. Some are faster than others, and some are less accurate. So what happened here was that they had individuals presenting to a COVID-19 testing facility. They had nasopharyngeal swabs, and they did the Roche SD biosensor rapid antigen test conducted in parallel with 2 real-time PCR tests, which they say is the reference standard. So obviously with all tests, you have to have some standard, otherwise you can't figure out what the prevalence of the disease actually is. But let's see what they tell us. So they find that using real-time PCR, which is the gold standard, they found a prevalence of 9.6% of whatever individuals presented to this facility. This was in, it's Swiss, so not the US. They found that the sensitivity was 65.3%, and the specificity was 99.9%. So with these numbers, if I took this rapid antigen test and I got a true, if I got a positive, what's the probability that I actually have the disease? So if I draw this again, 0.096, have disease based on the PCR test. 1 minus that would be 90.4. 90.4, I believe. Would not have the disease. Their sensitivity was 65.3, 0.653. And then 1 minus that, 0.347. So that's true, that's false. and their specificity was quite good at 999. That's false, and therefore 001 is true. So again, the probability of D, given that I get a true, is equal to probability that true, given disease times probability of having disease over probability of getting true, which again is equal to 0.096 times 0.653 over 0.096 times 0.05653 plus this path, 0.904 times 0.001. 0.096 times 0.653 divided by 0.096 times 0.653 plus 0.904 times 0.001. That is equal to 98.58%. So if I do get a positive with this test, then there is a 98%, almost 99% chance that I actually have the disease. So that's pretty good. That's pretty good. I mean, it's not good if I get a positive, but that's pretty accurate. But what if I say, what is the probability that I do not have the disease given that I get a false? And similarly, we've got false given as DC, probability of DC over probability of false. So then that would be F given DC, so that's this path divided by this path plus this path as well. So it's 0.904, 0.999 over 0.904, 0.999 plus 0.096, 0.347. Let's see, 0.0904, 0.999 divided by answer plus 0.096 times 0.347. Looks like 96.44%. So if I get a false, then 96% chance that I actually do not have the disease. It's pretty good. Of course, that's good, but there's possible that you do actually have the disease. So let's actually calculate that. The probability that you have disease, even if you have a false, this is just D here, D, FD 0.096 times 0.347, or 0.096. 0.096, 0.347 plus D given false, 0.904, 0.999. This should just be 1 minus whatever we got previously. That is equal to 3.56%. So yeah, it's just 1 minus what we got previously. So that's pretty good. Even though the sensitivity here looks quite low, because the prevalence is quite high, specificity is quite high, we see that if we get positive, then there's a good chance that we have COVID. If we get negative, there's a good chance we don't have COVID, but there is this almost 4% chance of a false negative, that even if we get a false, we do actually have COVID.